Learning objectives. In this chapter, the user would learn the following in detail. Different routing algorithms: DSR, AODV, TORA, CGSR. Mobile Internet Protocol, Packet Delivery and Handover Management, Location Management, Registration, Tunneling and Encapsulation, Route Optimization, Dynamic Host Configuration Protocol DHCP. Dynamic Host Configuration. Dynamic Host Configuration Protocol DHCP. When a mobile node visits a foreign network, it gets a new IP address, care of address COA, by agent discovery process and advertisement of the COAs by the foreign agent. Co-located COA is obtained by the Dynamic Host Configuration Protocol DHCP. Mobile computer, laptop or other visiting another network, a separate domain name server identity on the network and functions as a subnet on the internet. DHCP dynamically provides a dynamic IP address, subnet mask and ARP and RARP caches to enable the computer to transmit and receive the IP packets at the new IP address from the internet via the subnet. Server subnet has its own IP address to provide connectivity to the internet. DHCP, a protocol to dynamically provide new IP addresses, set subnet masks for the visiting computer, enables use of the server and subnet router at the place being visited, guarantees that any assigned network address is in use by only one DHCP client or none at a given instant. DHCP client. Software in an agent, for example, foreign agent for visiting mobile node. Device software for connecting to the network using a software component. Protocol communicates with a server. A number of steps in the DHCP protocol for dynamically configuring the client IP address and other networks. DHCP server. The server, software for allocation of network addresses to the computer. A number of DHCP servers at a subnet. A request is broadcasted to several servers. Server may be part of the operating system of the computer seeking connection to the network. Steps in DHCP protocol for dynamically configuring the IP address and other networks are as follows. Step 1. The DHCP client is an agent or device or computer broadcast DHCP discover, a discover request, directly or through a DHCP relay agent to the servers. Step 2. Each server listening to the discover request, DHCP discover, finds the configuration which can be offered to the client. Servers sense the configuration parameters including an IP address not presently in use at the subnet. The configuration parameters are in the DHCP offer for the offered configuration. Step 3. Client can reject the DHCP offer from a server or servers. When DHCP offers from all the servers are rejected, the client repeats the steps from step 1. Else step 4. Step 4. The client replies to the servers through a DHCP request to each server. The option reject is set in each reply to those DHCP servers to which the client reply is reject. The option select is set for those servers to which the client reply is select. Step 5. The selected DHCP server creates and manages bindings, binding a collection of configuration parameters including at least one IP address which is associated with and binds to the DHCP client. Sets a time interval during which the offered IP address will be valid for the DHCP client. The required interval can vary. Depends on the likely internet connection interval at a particular internet serving network. Step 6. The DHCP server confirms the binding through a message. It sends DHCPACK after creating the binding. Step 7. When the DHCP client computer leaves the subnet, it sends DHCP release message. In case the client does not send DHCP release within a specified time interval, the server frees the created binding. Step 8. The server and client also use the authentication protocols before considering the DHCP discover from a client and before accepting a DHCP offer, respectively. Handover Management. Packet Delivery and Handover Management. Correspondent node CN is an MN or a fixed IP host linked to a router which communicates IP packets to another MN in a home or foreign network when on visit. Various scenarios encountered in handover management are listed below. Case 1. CN, a fixed node and MNI at the home network. CN transmits message for connection, establishment or a packet using the IP protocol. CN IP header has source IP address and destination IP address of MNI in the same way as in case of IP protocol. HAI, the home agent for MNI, receives the message or packet and using the information that the distant MNI is at the home network itself, it delivers the message or packet to MNI. Receives the response message or packet from MNI. Delivers it to the CN using the IP protocol. Case 2. CN and MNK and MNI both at home network with agents HAK and HAL. MNK message for connection establishment or a packet using the IP protocol transmits through HAK. Same way as in case 1. The packet delivers to HAI and then to MNI. MNI responds like in case 1. HAK and HAI deliver the packets from one end to another and vice versa by just forwarding the packets to their respective MNs using the IP protocol. Case 3. CN is a fixed node and MNI is at a foreign network. CN transmits a message for connection establishment or a packet using the IP protocol. As in case 1. HAI receives the packets and uses the information that the destined mobile node MNI is not at the home network and is presently visiting a foreign network and is reachable via a foreign agent FAJ. HAI encapsulates the received IP packet using a new header, care of address COA, at the new header over the IP packet sent by HAI. Handover packet encapsulated with the new header with COA transmits to FAJ by tunneling. The FAJ reads the COA and decapsulates the IP packet, reads the destination IP address and transfers the packet to MNI. When MNI sends the response message or IP packet with CN as the destination address, FAJ transfers the packet to CN as would have been done by HAI in case the MNI is at the home network. The mobility of MNI is secured from the CN as any movement on the part of MNI is known only to HAI and FAJ. Case 4. CN is MNK and MNI at the foreign and home networks with FAK and HAS. The packet delivery process similar to the step in case 3. MNI transmits to CN, MNK delivers the packet to FAK. Here, FAK is used instead of HAK as now MNK is on a visit. FAK transfers the message to HAI like in case 1 where CN transfers the message to HAI. Mobile IP network employing home and foreign agents and packet delivery to and from a mobile node MNK at a foreign network with FAK and other mobile node MN1 at foreign network with FAJ. Case 5. CN, MNK and MNI at foreign networks with agents FAK and FAJ. MNK transmits to FAK. FAK to HAI. HAI to FAJ. FAJ to MNI. HAI to FAJ through tunnel TLJ. MNI responds to FAK. FAJ to HAK. HAK to FAK. FAK to MNK. HAK to FAK through another tunnel TKK. Case 6. CN and MNK at the home and MNI at a foreign network with FAJ. Case just opposite to the case 4. MNK transmits to the CN. FAJ delivers the packet to MNI. FAJ is used instead of HAI as now MNI is on a visit. FAJ transfers the message to HAI. Location management. Mobile node MN moves and thus visits foreign networks often. Handover management. Managing the transfer of service availability to the new location network. Preparing for the services. Packet receiving and packet transmitting at the new network entails use of appropriate location management protocols by the network for management of the MN's location. Agent discovery through agent advertisement. Advertisement of service availability from an agent and agent solicitation seeking service from an agent are two protocols used for discovering an agent by the MN. Agent discovery. MN must find a foreign agent FA when visiting a foreign network. Figure shows method of agent discovery by a mobile node MNI on receiving the COA care of address during agent advertisement or by agent solicitation in case the COA is not discovered. Steps in the protocol for discovering an agent are as follows. Listen to an advertisement ICMP message from an agent. Proceed to step 3 if the advertisement is found. Else, solicit the agent from the routers. If agent found, then proceed to step 3. Else, repeat the step. If the COA discovered from the message is found to be the same as the previous COA, go back to step 1. Else, proceed to step 4. If the discovered COA is the same as the home network, deregister at this network and go back to step 1. Else, if the current COA is a new COA, then register with the new COA. Agent advertisement. Agent advertisements used by MNs to discover home and foreign agents while moving from one network area to another. Essentially, ICMP message sent to a number of addresses. ICMP messages uses following options and words added for mobility extension of ICMP header. 132-bit word format. First byte is equal to 00010000. Second byte for length is equal to 2 words plus number of COAs specified in the extension to which the ICMP message is to be sent, and 2 bytes for the 16-bit sequence number for the ICMP message advertised. 32-bit word has 2 byte specification by the agent for registration lifetime, during which MN can register, in which the new COA, step 4 in agent discovery. Lifetime specifications is in seconds. Has 8 bits for flags. Remaining byte is not used. It is reserved for any future requirements of modifications or specification expansion in ICMP. Set of 32-bit words for the COA addresses for the MN at that agent. Second word has 8 flag bits. COA is said to be the co-located COA when the MN acquires temporarily an additional IP address while on visit to a new network. Else, the COA is the same IP address for that MN while on visit and when at home. FA obtains the co-located COA using the Dynamic Host Configuration Protocol DHCP. Flags. Flag 1. Whether the COA is a co-located COA. Flag 2. Whether the advertising agent is the HA. Flag 3. Whether the advertising agent is an FA. Flag 4. Specifies whether there is reverse tunneling support by the FA for encapsulation and sending packets by tunneling to the HA. Flag 5 specifies whether the encapsulation method is generic. Flag 6 specifies whether the encapsulation method is a minimal mandatory method. Flag 7 specifies if the agent is busy and cannot register the visiting MN. Agent solicitation. If an advertisement is not listened to, solicitation can be done 3 times at 1s intervals. Later, this interval can be increased. Agent solicitation is a method by which an MN visiting a network discovers the FA and the COA. Mobile Internet Protocol. Introduction. The Internet Network Layer Protocol IP is the widely used network protocol today. Mobile IP network layer facilitates internet-based communication between mobile nodes, MNs. IP and mobile IP network layers. OSI, Open Systems Interconnection, defines 7 layers for data communication. TCP/IP is the most widely used models, having 5 layers. Network layer, layer 3, uses IP in this model. OSI, Open Systems Interconnection, 7-layer model. The figure below shows the 7 layers of OSI. OSI, Open Systems Interconnection, 7-layer model. Physical layer, L1, for sending and receiving signals wirelessly. Example, TDMA or CDMA coding with FEC or over wire or fiber. Data link, L2, for linking to the destination computer by MAC address. Network, L3, for routing through a chain of routers. Transport, L4, for defining, sequencing, and for repeat transmission. Session, L5, for defining the transaction and session protocol for establishing end-to-end connectivity. Presentation, L6, for defining the data encoding format. Application, L7, for running a web browser, mail transfer, or mobile e-business application. L7 to L1 data transmission. A physical network transmits data of one end application L7 to another end application L7 through the various intermediate layers. At a layer, data received from the upper layer can be suitably divided, for example, packetized at the L3 IP layer. At each layer, data or each section of data suitably encoded, for example, by adding a header for transmission to the lower layer. L1 to L7 reception. At the receiving end of the network, the bits in the header fields are decoded, for example, by extracting the header upon reception before passing the data to the upper layer. L2 and L1 layers, usually associated with the communication and physical network radio and switching infrastructure, for example, in GSM or CDMA systems. L3 layer, for networking, using a path chosen among the large number of paths available through a chain of in-between routers. IP protocol, mobile IP protocol. L4 layer, data transfer after a session is established through the session layer L5 between two ports on the networks to the L4. The protocol header fields of this layer define the sequences and other required fields for data transfer to and from a port in a network. L5 layer defines how various sessions are established, for example, a call setup session. Not present in the TCP/IP model does not provide for a separate session layer and establishment and close functions included at L4. L6 layer defines how the data from the port is to be presented or formatted. Not present in the TCP/IP model does not provide for a separate session layer and presentation functions included at L7. L7 layer supports multiple applications. Defines a protocol for transferring application contents and data of a port. Each port application defines a service access point at the L7 layer. Each port deploys a protocol for data transfer between the L7s at the transmitter and the receiver. An output port transmits the service application contents and data employing a distinct protocol. Example: HTTP, Hypertext Transfer Protocol. A corresponding data input port software at the receiver L7 layer, service access point. Same protocol used to retrieve the service application contents and data as during transmission. Example: HTTP, Hypertext Transfer Protocol. A port number can be defined for each application. A port can be numbered in order to define and distinguish each application's data easily. Example: HTTP port in the TCP/IP model, through which all the HTML files are transferred through the network, is numbered 80. The below figure shows OSI layers quick summary. Internet Protocol IP. The basic protocol at L3, which is used for transmission over the Internet. Designed for use by networks which employ packet-switched data communication. Provisions the transmission of data packets. Each packet treated independently. Every packet must contain complete destination addressing information. Packet formation in IP. Packets of maximum size is equal to 216 bytes 214 words after the data from L4 transport layer divided. A packet switched network can be used for transmission. Hopping of data packets use different routes to reach a destination. More packets can be sent simultaneously through the network, unlike in a circuit-switched network where only one data frame can be transmitted at an instant, for example, in GSM or HSCSD. Header, source and destination IP addressing. IP specifies certain header fields. A field is a set of bits placed in a word for a specification, condition or purpose. Encoding data from the transport layer at the transmitter. Decoding the data received from the data link layer before passing it to the transport layer at the receiver. Header fields are as follows. First word. 32-bit word to specify IP version, IPv4 or IPv6 for Internet or broadband Internet. Length of the IP header. Precedence of the IP packet. Total packet length including L3 layer for encoding. Second word. 32-bit word. ID for the packet. Flags. Fragment offset for the fragments of same ID. Third word. 32-bit word. Time to live, not in seconds but in number of attempts to hop before expiry of packets in the network. Type of protocol. Checksum of the header for finding transmission errors if any. Fourth word. 32-bit word. IP address of the source as per 4 decimal numbers, each separated by dots and each lesser than 256. Example. Source IP address for routing is ns1.ns2.ns3.ns4. Fifth word. 32-bit word. IP address of the destination. 4 decimal numbers, each separated by dots and each lesser than 256. Example. Destination IP address nd1.nd2.nd3.nd4. Packet transmission from the source IP address to the destination. By hopping among the various routers on a path. Paths can be different for different packets from the same source. Path for the routing of a packet depends on the paths and subpaths which are available in the network at a given instant. Point-to-point, multicast and broadcast. Point-to-point or unicast transfer. Message or packet transmits to the destined IP address only. Multicast transfer. Message or packet transmits to a group of IP addresses. The IP protocol specifies the use of a Class D subnet for multicasting. Multicasting subnet has 4 MSBS 1110 in the net ID part of the IP address for defining subnet as multicast network. 32 minus 4 is equal to 28 bits specify the address for the multicasting net ID and the subnet and host S and R addresses. The address 224.0.0.1 multicast to all hosts in the links of a router. NS1 is equal to 224 in decimal system is equal to 111,000,000 in binary system. Multicasting can be used for flooding a UDP, User Datagram Protocol on the network. Flooding is required for advertisement. It means sending information along many paths. Panning tree protocol, protocol to block nodes which have already received the relevant information during flooding. Multicast tree. A multicasting source route multicasting to select multicast nodes subnets at level 1. Each level 1 node then transmits to multicast nodes subnets at level 2 and so on. A hierarchy of nodes present in a multicast tree. Multicast tree nodes at one level can transmit to multicast nodes at another level simultaneously via multiple paths. Time taken in multicasting a message is greatly reduced. Broadcasting. Message or packet transmits to all the IP addresses which are set for listening. The IP protocol specifies an address for broadcasting. All 32 bits. One is 255.255.255.255. Used when broadcasting to all hosts and links of a router. User Datagram Protocol provides independent information. A datagram is stateless, not necessarily a sequential successor of a previous one or a predecessor of the next. Data is sent using a connectionless protocol. Connectionless protocol. No session establishment before the data. Transfer begins. Example, on phones there are hotlines where one can just speak without the usual dialing and waiting business. Consists of maximum of 216 bytes transmitted as sequence of words, each of 32 bits, 4 bytes. UDP header fields consist of the following: source port number, destination port number, source IP address, destination IP address, length of data. Checksum bytes for the header to check erroneous receipt of header. Internet Control Message Protocol ICMP. Another connectionless protocol, a part of the IP network protocol suite. ICMP uses a datagram which has an ICMP header when sending the messages for querying to find information, reporting errors, making root address advertisement, routers soliciting messages to get the IP addresses of the linked subnets. ICMP header. First word of 32 bits to specify a byte for type of message, a byte for the code, and 2-byte checksum. Second word of 32 bits which specifies the number of addresses for advertising along with the address field size and the lifetime of message validity. A set of pairs of words, each specifying router address and preference. The pairs arranged in sequence for level 1, level 2 and so on in a tree. Router of high preference gets the messages earlier than the others. Extended words in headers are called options. First byte is equal to 16 means that options being used. One example of option use is the mobile IP protocol extension when an agent advertises. Mobile Internet Protocol, mobile IP. A protocol developed to allow internet work mobility for wireless nodes without them having to change their IP addresses. Mobile IP is defined by the Internet Engineering Task Force IETF, described in the IETF RFC 3344. Evolution of mobile IP. When a user computer, example laptop, moves from one place to another, it is assigned a new IP address at the new hosting subnet to which the service providing router provides connectivity to the internet. A mobile node can be considered to be computer on the move from one area to another. Reasons for use of new mobile IP protocol instead of existing IP by the MNS. Need for enhancing IP network capacity. Security needs. Need for non-transparency from higher layers. Need for enhancing IP network capacity. Use of the existing IP protocol by the large number of mobile nodes MNs will lead to a decrease in the network throughout unless the capacity of existing IP network is scaled up to cater to such a large number of users. When mobile nodes to move from one place to another while using the existing IP protocol, new protocols are required at the data link and physical layers. IP network protocols support 48-bit MAC addresses, but when the number of MNs is large, then other interfaces and lower-level protocols required. Security needs. The mobility of the called MN must be hidden from the calling MN. When a new IP address allocates at the new hosting subnet of the existing IP-based infrastructure, the identity of the mobile node is not hidden from another host. The MN exposes and lacks security when using the existing IP protocol. Need for non-transparency from higher layers. The transport layer establishes a connection between a given port at a given IP address called socket with another port at another IP address. The connection, once established by the transport layers between the sockets, is broken as soon as the new address is assigned. Problems due to non-transparency from higher layers are: re-establishment of the connection takes time, which means loss of data during that interval. Re-establishment process has to share the same network and the given transmission rate. Any movement of the MN will be transparent to the TCP and to L7 in case the TCP layer re-establishes the connection when the IP protocol used by the MN. There is, therefore, a need for non-transparency of the MN to distant ports. Example of non-transparency from higher layers. Assume a distant router is sending data packets for an IP address presently assigned to a mobile terminal using another router. When the terminal moves from one service area to another, the routing tables on the route need to be updated. Till this is done, the packets will not reach their new destination. This case needs are following. The reconfiguration messages for updating the routing tables have to share the same network and the given transmission rate. Re-establishment of the connection takes time, and this means loss of data during that interval. Any movement on the part of the MN is transparent and thus not secure from the distant host on the network of distant routers. Working of mobile IP. Figure shows architecture for a mobile IP network. It shows how a mobile IP network employs home and foreign agents. A mobile node MN connects to a mobile services switching center MSC in the radio subsystem. An MN can access internet services using the mobile IP protocol. The MN can change its service router when visiting another location which is serviced by a different router. A router has a home agent HA for a set of home networked MNs as well as foreign agent FA for the visiting MNs. An agent, software employed at a router or the host serviced by a router. The same software can function as both the HA and the FA at different instants of time. An MN can also have software which functions as an FA instead of the FA at the router. The HA and the FA play a location management role similar to that of the HLR and the VLR in a GSM system. Switching Center Home Agent. Switching Center has a home agent HA in a home network. HA provides services to an MN at the registered home network, including transmitting and receiving packets from the Internet. A home agent assigns MNs to routers which support the MNs. A home network is a mobile radio subsystems network with an area called paging area. A home network is like a subnet. Just like a subnet has a number of IP hosts, a home network has the MNs. Paging area is the area in which the MNs of home as well as foreign networks can be approached through a single MSC or a set of MSCs. Routing of packets through the routers is performed when an MN moves within one paging area. Switching Center Foreign Agent FA. Another switching center as a foreign agent for a foreign network of visiting MNs. Foreign network, another mobile radio subsystem network which the MNs of home network visit within the paging area. Foreign agent, a provider of the IP address and services including transmitting and receiving packets from the Internet for MNs on visit to a foreign network. Foreign agent assigns MNs to a router which supports the MNs of other home networks. Different paging areas interconnected through gateway routers form a backbone network. Rerouting of the packets done through the gateway routers when an MN moves from one paging area to another. Registration. When an MN discovering FA for service and finding a COA, MN needs to register for the service of receiving and transmitting of IP packets with a new agent FA. MN must also deregister for the receiving and transmitting of IP packets with a HA, step 4 of agent discovery in the protocol. Function of HA after registration is to encapsulate the IP packets and transmit them to the discovered FA through tunneling whenever a CN corresponding node communicates with the MN. Figure shows a mobile node MNK at a foreign network after agent discovery of FAJ seeking registration for creating tunnel between HAI and FAJ. Requests and replies are made by the MN, FA and HA using a UDP datagram. Let us assume that the MN has IP address of the HA. If not, then the MN broadcasts the registration request to a paging area. The HAs then send the registration replies. The MN requests one of the HAs out of those which reply for registration. Registration steps. Step 1. The MN sends a registration request to FA. FA sends that request to the HA. When the COA is a co-located COA, then the request sent directly to the HA. Step 2. The HA binds itself for mobility, binds itself for encapsulating and tunneling the packets to the MN through a new FA. The binding period equals the lifetime of the COA. Step 3. The MN registers again before the binding period expires when it moves to another foreign network or when it returns back to the home network. Step 4. The HA sends a registration reply to the FA and the FA to the MN. The MN checks whether the reply shows successful registration. Means that mobility binding now exists from the HA to FA. Possible that reply shows that registration was not successful. Failure. When there are too many tunnels created at the HA and the HA does not have the resource to handle new requests, or there is an authentication failure, or the HA not reachable to the FA. Registration request fields for sending. Mobile IP registration is by a UDP datagram, which sends the request using following words after UDP header. One 32-bit word with first byte is equal to 00000001. 8 bits for flags and 2 bytes for the lifetime in seconds. Next 32-bit word for the home IP address of the MN. Next 32-bit word for the home agent IP address of the MN. Next 32-bit word for the COA of the MN at the new agent. Next 32-bit word for the identification of the MN. Next, a set of words for extensions. 8 flag bits in first word. Flag 1 specifies whether the COA is a co-located COA. Flag 2 whether the advertising agent is the HA. Flag 3 whether the advertising agent is the FA. Flag 4 specifies whether the MN requests previous mobility binding to be retained. This permits both the new and previous mobility bindings. Flag 5 specifies whether the encapsulation method is generic. Flag 6 specifies whether the encapsulation method is a minimal mandatory method. Flag 7 specifies whether the MN wishes to receive broadcast multicast messages which the HA receives for tunneling to the new FA. If not, then the broadcast messages are filtered at the HA. Flag 8 specify if there is reverse tunneling support from the FA. Registration reply fields for sending. UDP datagram sends reply using the following words after the header. 32-bit word with first byte 000000011. 8 bits for a code specifying the result of registration and 2 bytes for the lifetime in seconds. Next 32-bit word for the home IP address of the MN. Next 32-bit word for the home agent IP address of the MN. Next 32-bit word for identification of the MN. Next, a set of words for extensions. Result of registration at the code sent in the first word of the reply indicates successful registration and whether the previous mobility binding still exists. FA's rejection with one of the 5 reasons for it. HA's rejection with one of the 6 reasons for it. New database entry fields after registration at the HA consists of the following: ID for identification of MN, COA of the MN, lifetime of binding to tunnel the package to the MN's COA. When the binding life expires, the tunnel is not forwarding from the HA to the FA using the COA. Database entries in the fields at the FA after registration at the HA. Following are the entries for the MNs visiting at the FA. MN identification field, home IP address of the MN, IP address of the HA, MN link layer address for sending and receiving packets and messages to and from the MN, UDP source port of the registration request, received identification of the MN, COA of the MN, and lifetime of binding to tunnel the packets to the MN's COA, remaining lifetime. Route optimization. Consider the above figure. Assume that MNI is visiting a foreign network which happens to be the home network of CN2 and CN2 is very close to CN. Consider mobile IP network employing home and foreign agents and packet delivery to and from the MNK at a foreign network with FAK and MN1 at the foreign network with FAJ. Figure below shows a mobile IP network employing a triangular route without mobility binding between COAJ and CNK. It marks the path numbered in sequence as 1, 2, 3, 4 and 5 to MNI. Packets make a triangular trip to reach from CNK to MNI. Also possible that FAK and FAJ are identical. Optimization of route for the triangular routing example can be made in case the MNI opts to make its mobility known. Mobility binding. Triangular route optimization to a direct route is performed as follows. If MNI permits identification of its mobility when it visits a foreign network, then CN can use a mobility binding cache. Mobility binding cache stores the current COA of the called MN. CN can directly send the IP packets to MNI instead of triangular routing through HA1, then to the COA through the tunnel. Figure below shows route optimization and path 1, 2, 3, 4, 5 after binding of MN1 with COAJ with CNK. Also marks the steps for establishing route optimization. Mobility binding steps in the calling network. CNK fixed or MNK mobile network sends a mobility binding request to HAI. HAI detects whether MNI for which binding request is made has blocked external mobility binding request. If not, then HAI sends the update for the mobility binding message to the CNK network. External does not include the visiting network FA. Mobility binding message has the IP address of MNL and the present COA, COAJ of MNL when on visit to a foreign network and registered with FAJ. CNK issues an acknowledgement to HAL on receiving the binding message. CN2 network decapsulates the IP packet. This decapsulation would have been performed by FAJ through HA1 if MN1 had blocked external binding requests and sends a warning for binding. Optimization for smooth handover. FAJ sends a binding warning to CNK when MNL deregisters with it. Let's CNK initiate another binding request to HAL of MNL. CNK gets the new binding and COAM address from HAL in the binding cache. Reverse tunneling. If a reverse tunnel is formed, then another tunnel is present through the paths from 10 to 3. Reverse tunneling from FA to HA. Advantage of reverse tunneling is multicasting using bidirectional tunneling method. Reverse tunneling is required when a firewall is employed. Multicasting. Bidirectional tunneling refers to tunneling from the HA to FA and reverse tunneling from FA to HA. Facilitates multicasting to a mobile node. Information is multicast to an MN when it sets the option for multicast listening. This method works in the following manner. Assume that MNL visits a foreign network with FAJ. Multicast tree multicasts a packet to HAJ. HAJ forwards IP packet to MNJ. This is done after registration. HAJ establishes a bidirectional tunnel between HAL and FAJ. HA transmits received multicast message or packet to MNJ. If MNL visits another foreign network with foreign agent FAK, MNL requests FAK and FAJ forwards the transmit request for the multicast to FAJ. Disadvantages of this approach are as follows. Duplication of multicast IP packets takes place. IP packets reach by short and long paths when there is no DMSP. When DMSP provides multicast service, IP packets reach by longer path as the longer path as the DMSP route may not be shortest. Advantage is that there is no configuration, updating of routing tables of routers at multicast tree. Remote subscription approach. Another multicast approach. Assume that MNL visits a foreign network with foreign agent FAJ. FAJ transmits a join request in case it is no registered for multicast. Advantage is that there is no duplication of multicast IP packet and IP packets reach through an optimal shortest path. When MNL moves to next foreign agent FAK, it again transmits a join request and subscription is cancelled. Firewall security. Filters packets assigned to an IP address received from another IP address. IP address of the MN is at home agent. When it moves to a FA, MN sends the IP packet using the care of address COA assigned at foreign agent. Then, firewall permits another IP address at the FA assigned to an IP address at the HA. Thus, there is a security risk. This is because when there is reverse tunneling of the packet from the FA COA to home agent and it transmits to correspondent node CN, then firewall gets the packets from same IP address as the IP address registered at the firewall and it does not filter these packets. Time to live. Time to live defines the number of attempts to hop before expiry of packets at the network. GRE header encapsulation during tunneling sets time to live is equal to 1, so the packets are forwarded only once. The tunnel does not need extra hops as fixed endpoints. Results in once only forwarding through the tunnel from the home agent HA to the foreign agent FA when the mobile node MN visits a foreign network. At the foreign agent, the time to live setting might be too low. Therefore, when the MNL sends the response to the correspondent network CNK, then the time to live set at the FA may not be sufficient. When the COA is used to send the response to the CN without reverse tunneling, then a very low setting of time to live blocks the packets after a very small number of hops attempts to the CN. Reverse tunneling also sets the time to live equal to 1 because IP packets need to be sent only once. The tunnel does not need extra hops. It has fixed source and destination endpoints. Reverse tunneling facilitates guaranteed transmission of the IP packet responses through the tunnel to the HA. Now, the HA transmits the response to the CN. A low value of time to live at the FA does not lead to packet expiries. Routing algorithms. Router. Terms and process involved in sending packets from a source to a destination. A router is at a node and receives packets from a neighboring node router source and forwards packets to another neighboring node router towards destination at a given instance. Each router maintains a routing table. Table must maintain an update in the rows, the destination and neighboring node addresses for that destination. Each router routing table catches the destination information regularly. Purpose of routing table is that it provides the presently available active paths for destination so that packet received from source is forwarded to another node in active path towards destination. Each router receives RREQ, route request packet, from a source so the source can discover forward paths for the destination. Router catches the RREP, route reply packet, from reverse paths from destination. Then it updates the route information in the table for each connected destination. Sends a RERR, route error packet, to the source when a previously active path to destination has developed link disconnection at an instance. Routing algorithm. Algorithm used for service discovery and for caching, maintaining and updating the routing table. Ad hoc networks are deployed for routing, target detection and service discovery. Routing protocol specifies the method used and phases sequences deployed for maintaining and updating the routing table at the nodes in the network. Following are some of the routing protocols: Dynamic Source Routing Protocol (DSR), Ad hoc On-Demand Distance Vector Routing Protocol (AODV), Temporarily Ordered Routing Algorithm (TORA), Cluster Head Gateway Switch Routing (CGSR), Dynamic Source Routing (DSR) protocol. Deploys source routing. Each node caches the specified route to destination during source routing of a packet through that node. This enables a node to provide route specification when a packet source routes from that node. Each node deletes the specified route to destination during routing of error packet in reverse path to the source in case of observing a disconnection during forward path to destination. The deletion of link shown in a table or cache is called link reversal. Source routing means that each data packet includes the routing node addresses also. Reactive protocol reacts to the changes and dynamically maintains only the routing addresses from source to destination, which are the active paths to a destination at a given instant. Performs unicast routing. Unicast means routing packets to a single distant address. Phase in DSR protocol. There are two phases, phase 1 and phase 2 for source routing, caching of specific route addresses, reversal process of route address specifications. Phase 1 in DSR protocol. Source node initiates a route discovery process. It broadcasts the packets, each with a header. It then expects return of acknowledgement from each destination. The packets are called route request (RREQ) packets. DSR uses flooding, sends multiple RREQs. A header for each route request packet has the unique request number and source and destination addresses. This enables identification of request at each intermediate node in the request and acknowledgement packets. When the process starts, initially only the source address is given in the header. When the packet reaches a neighbor, that is, any intermediate node, the node adds its own address in the header if it is able to successfully send the packet to its next neighbor. When the packet reaches the destined address, its header therefore has all addresses of the nodes in the path. When packet reaches the destination, a route reply RREP for the sequence used in RREQ is generated. On return path, the route cache builds up at each intermediate node for deployment at a later instant of phase 2. Example: assume that node D is a source and G is a destination, and the path D, E, F, G is not known. In such a case, the path cannot be placed in the header. Source header from D puts the sequence number Q and source address D in the packet header and sends the packet to its next neighbor. When the packet reaches E, its header is QD. Assume that no root error packet bounced back from neighbor E. The packet is then transmitted to F. When the packet reaches F, its header is QDE. Assume that no root error packet bounced back from neighbor F. The packet is transmitted from F to G. Assume that no root error packet bounced back from neighbor G. When the packet reaches G, its header is QDEF. Phase 2 in DSR. When any source node desires to send a message, it first looks at its root cache. If the required route is available in cache, the source node pulls all the addresses of the nodes for the path to destination in the header. Example: assuming that there is a message from a MANET node D in the network, node D, destination A, cached path DCA. Node D, destination B, cached path DCAB. Node D, destination F, cached path DEF. Node D, destination G, cached path DEFG. The path specified at a source is dynamically modified when an alternative path to a destination has to be followed. The alternative path is cached when there is a root error packet generated in the reply. Ad hoc on-demand distance vector AODV routing protocol. A reactive protocol. Reacts to the changes and maintains only the active routes in the cache or tables for a pre-specified expiration time. Routes that are found are expected to be available at a given instant. Performs unicast routing. Distance vector means a set of distant nodes which defines the path to destination. For example, DEFG is a distance vector for source-destination pair D and G. In AODV, a distance vector is provided on demand during forwarding of a packet to destination by a node in the path and not by the root cache providing path through the header in the source data packet phase 2 in DSR. Every node keeps a next hop routing table which contains the destinations to which it currently has a route. A routing table entry expires if it has not been used or deactivated for a pre-specified expiration time. Ad hoc on-demand distance vector AODV routing protocol. AODV adopts the destination sequence number technique. Does not deploy flooding multiple RREQs. Stores the next hop routing information of the active routes in the routing caches tables at each node. Therefore, has small header size and thus reduces the network traffic overhead. Phase 1 in AODV protocol. A node uses hello messages to notify its existence to its neighbors. Therefore, the link status to the next hop in an active route is continuously monitored. When any node discovers a link disconnection, it broadcasts a root error (RERR) packet to its neighbor, who in turn propagate the RERR packet towards those nodes whose routes may be affected by the disconnected link. Then the affected source can be informed. Phase 2 in AODV protocol. Source node initiates a route discovery process if no route is available in the routing table. It broadcasts the demand through the RREQ packets. Each RREQ has an ID and the addresses of the source and destination in its header. It expects written acknowledgement from destination. A node identifies the last observed sequence number of the destination from the ID. Each RREQ starts with a small TTL, time to live, value, number of attempts. If the destination is not found during the TTL is increased in subsequent RREQ packets. The node also identifies sequence number of source node. Sequence numbers ensure loop-free and up-to-date routes. Loop-free means free from bouncing of a packet to a node after intermediate hops. Each node rejects the RREQ which it had observed before. This reduces flooding, which means it reduces too many RREQs present in the network at a given instant. Route table in AODV keeps entries for a specified period, and each node maintains a cache. The cache saves the received RREQs. Only the RREQ of highest sequence numbers are accepted and previous ones are discarded. The cache also saves the written path for each RREQ source. When a node having a route to the destination or the destined node receives the RREQ, it checks the destination sequence number it currently knows and the one specified in the RREQ. RREP packet is created and forwarded back to the source only if the destination sequence number is equal to or greater than the one specified in RREQ. It guarantees the updating of routing cache information. Uses only symmetric lines and RREP follows the reverse path of respective RREQ. Each intermediate link on receiving the RREP packet updates the table discarding the previous entry and forwards back the RREP to its neighbor in path to the source. Temporarily Ordering Routing Algorithm (TORA), a reactive protocol, reacts to the changes and link reversals. Employed for highly dynamic MANETs and provides an improved partial link reversal process. Discovers the network portions showing the link reversals. Has a feature that it stops the non-productive link reversals in a given portion of the network. Assumes addresses of the routers in the path and of source and destination for one set of input route. Each node provides only one set of subsequent route addresses. Network shows a directed acrylic graph topology, means one input path and one outgoing path. Possesses network capacity such that many nodes can send packets to a given destination. Guarantees loop-free routes, no bouncing of a packet to the node once it transmits to intermediate hops. Supports multicasting from one source to multiple destinations. Unlike AODV, but similar to DSR, TORA supports unidirectional links and also provides multiple routing paths. It does not exchange hello messages periodically to listen to disconnected links as done by AODV. Phase 1, 2 and 3 in TORA are route creation, route maintenance and productive useful link reversals, vector discarding. Cluster head gateway switching routing CGSR. A hierarchical routing protocol. Proactive protocol. When a source routes the packets to destination, the routing tables are already available at the nodes. A cluster higher in hierarchy sends the packets to the cluster lower in hierarchy. Each cluster can have several daughters and forms a tree-like structure in CGSR. Forms a cluster structure. The nodes aggregate into clusters using an appropriate algorithm. The different clusters can be assigned to different band of frequencies in FDMA or different spreading CDMA codes. CGSR algorithm defines a cluster head, the node used for connection to other clusters. Also defines a gateway node which provides switching, communication between two or more cluster heads. Three types of nodes in CGSR. Internal nodes in a cluster which transmit and receive the messages and packets through a cluster head. Cluster head in each cluster such that there is a cluster head which dynamically schedules the route paths. It controls a group of ad hoc hosts, monitors broadcasting within the cluster, and forwards the messages to another cluster head. Gateway node to carry out transmission and reception of messages and packets between cluster heads of two clusters. Cluster structure. A higher performance of the routing protocol as compared to other protocols because it provides gateway switch type traffic redirections, and clusters provide an effective membership of nodes for connectivity. CGSR. Phase 1, 2 and 3 of CGSR are routing path discovery and caching, maintaining update and distribution respectively. The basic processes of CGSR are cluster definitions and selection of clusters for routing. Algorithms are used for both the processes. Phase 1. Routing path discovery and caching. Each node maintains a routing table that determines the next hop to reach other clusters. An algorithm that can be used in this phase is the Destination Sequenced Distance Vector (DSDV) algorithm. That means it finds the next hop to the distance destinations. Cluster member table is created using sequence numbers in RREQ packets which are broadcast periodically. Phase 2. Maintaining routing information. A clustering algorithm used for maintenance of routing information is least cluster change (LCC). Cluster head changes only when one of the nodes moves out of range of all cluster heads in the cluster or two cluster heads come within one cluster. A token-based algorithm can be used to control the transmission within a cluster. Cluster head should get more chance to transmit as it is in charge of broadcasting within the cluster and of forwarding packets between nodes. Cluster heads are given priority such that route path utilization is maximized and packets are transmitted with minimum delay. Another algorithm is the priority token scheduling (PTS), which gives higher priority to neighboring nodes from which a packet was received recently. Each node dynamically maintains a cluster member table. Algorithm is such that node will periodically change entries in its cluster member table when a new sequence number entry is received from neighbor after successful RREP. Table rows map each node to its own cluster head. Node transmits its cluster member table periodically. After receiving broadcasts from other nodes, node uses a DSDV algorithm to update its own cluster member table. Tunneling. When a mobile node MN is visiting a foreign network supported by a foreign agent FA, then the FA has the COA care of address of the MN. The FA receives the IP packets that were received at the home agent HA through a tunnel from the HA to the FA, from HA IP address to the COA IP address at the FA. Tunneling refers to establishing of a pipe. Pipe, a data stream between two connected ends. The data stream, inserted from one end and retrieved as FIFO, first in first out words, from the other end. Packets received at the HA are transmitted through the tunnel after encapsulation. Figure shows a tunnel between the HA and FA to carry the encapsulated packet. Figure shows three ways of encapsulation. Encapsulation by additional IP header of an IP packet over the IP packet received at the HA. Maximum 216 byte IP packet. New IP header. The IP address of the HA as the source and the IP address of the FA as the destination. Format of encapsulated data. First 32-bit word to specify the IP version, IPv4 or IPv6 for Internet or broadband Internet. Length of header is equal to 5 words, precedence of the packet, and total packet length, which is now 5 words more than that of IP packet received at the HA. Second 32-bit word to specify the ID for the packet, flags, and fragment offset for the same packet ID. Third 32-bit word to specify the time to live, number of atoms to hop before expiry of packets at the network, type of protocol, checksum of the header for finding transmission errors if any. Fourth 32-bit word, 4 decimal numbers separated by dots and each less than 256 to specify the IP address of the home agent. Fifth 32-bit word, 4 decimal numbers separated by dots and each less than 256 to specify the IP address of the destination, COA, care of address. 6th to 10th words are the IP header of 5 words with the 4th word as the IP address of the correspondent node CN and the 5th word as the IP address of the MN. IP packet data received from the transport layer at the correspondent node so that each packet has a maximum of 216 bytes. Minimum encapsulation ME method by IP header to an IP packet. Combines header of 10 words specified into 7 or 8 words in the following manner. First words in the new IP header of 5 words and the IP packet header of 5 words are the same and are duplicating in case of IP in IP encapsulation. The 6th and 7th words in the 6th item of the new IP headers are not present in ME as both words are mere repetitions. The 8th word in the 6th item changed and now specifies the type of protocol, a 1-bit flag, 7 reserved bits, and a 16-bit checksum of the modified 3-word IP header from the original 5 for finding transmission error, if any. The 9th word in the 6th item changed and now specifies, instead of the CN IP address, the MN IP address which was earlier specified by the 10th word. The 10th word in the 6th item changed and now specifies, instead of the MN IP address, the CN IP address in case of the flag bit is set to 1 and the 10th word in the 6th item is removed in case the flag bit is set to 0. FA reads the first 5 words in ME and transmits the packet to the MN using the COA. The MN IP address is specified by the 7th or the 8th word depending upon the flag bit. Generic Routing Encapsulation (GRE) by IP header to IP packet. IP header in IP header encapsulation and ME methods have the following deficiencies. Routing information for tunneling not given. No provisions for recursive encapsulations. Recursive encapsulations needed when the tunnel transmits multiple pieces of information for the MN and each piece of information encapsulates in one protocol. No provision for a key that can be used for authentication or encryption. One or more GRE headers depending on the number of recursions required to send multiple pieces of information. Three components in GRE encapsulation method are described below. New IP header. Same as the first to fifth words in the first to fifth items of the new IP header. Time to live is however set as 1. Results in once-only forwarding to the FA by the HA. The tunnel does not need an extra hop attempt, so time to live can be set to 1. Tunnel does not get blocked like routers due to external IP address transmissions. Has fixed source and destination endpoints. GRE headers. There is one GRE header for each protocol for encapsulation. GRE header can be sent recursively after the new IP header. The sixth 32-bit word in encapsulation and the first word of the first GRE header. 16-bit flags. Bits to define the number of recursions, reserve bits, and version bits. Next 16 bits specify the protocol for encapsulating the information sent with the GRE header. The seventh word specifies a 16-bit checksum and a 16-bit offset. Both are optional as indicated by the flag bits used to define these options. The eighth word, a 32-bit key, optional as indicated by the flag bit to used define the key option. The key at the GRE header enables authentication or encryption at the FA. The ninth word specifies a 32-bit sequence number information, optional as indicated by the flag bit used to define the sequencing option. Sequencing at the GRE header enables the FA to rearrange the packets sent by the HA. The 10th word specifies a 32-bit routing information, optional as indicated by the flag bit used to define the routing option. Routing at the GRE header enables use of routing information at the FA. 11th word onwards. If number of recursions are defined in the first word of the GRE header, then the next GRE header is inserted before the IP header and IP data sent by the HA. If number of recursions specified in the 11th word in the GRE header is 2, then the next two GRE headers are also inserted before the IP header and IP data sent by the HA. IP header and IP packet data. This part remains the same as that is the unencapsulated IP header and the data received from the CN correspondent node IP packet at the HA. The first word has 5 flag bits and 3 recursion number defining bits. The 5 flag bits are checksum option flag, sequence number field option flag, key option flag, and source routing option flag. Source routing is a method in which source of a packet provides the route information. Router uses the routing information word for routing a packet. Conclusion. In this chapter, we have covered the following in detail. Different routing algorithms: DSR, AODV, TORA, CGSR. Mobile Internet Protocol, Packet Delivery and Handover Management, Location Management, Registration, Tunneling and Encapsulation, Route Optimization, Dynamic Host Configuration Protocol (DHCP).